Okay, hello students. What you see in front of you is all of the equipment needed to study the photoelectric effect. So what I'll do is I'll take you through each component and we'll go from there. To start with, we have a light source over here, and what the light source is actually just sort of a common physics lecture demonstration. It's sort of a big black metal tube that has a bunch of LEDs mounted on it. And you can turn this knob here to select what LED you want to come on. So at the moment it's green. If I go over here, I can choose something yellow and orange and on into the reds. And if I turn it back the other way, I can visit some of the blues and the violets. So you might think the LEDs are a bit pedestrian and maybe you'd rather use something like a laser, but they're actually a rather convenient source of multiple narrowband wavelengths. As you know, LEDs are quantum devices with a well-defined band gap, and when energized, they emit a well-defined wavelength, plus or minus some bandwidth, as we'll see. But they're absolutely ideal for an experiment like this, where we need a source of multiple narrowband wavelengths. Next, what happens is as the light leaves the LED, it hits a lens here, which focuses the light somewhat over here on this metal box. And the metal box, of course, contains a small glass bulb, which I'll show you in a subsequent video, that contains the photocathode. And so, of course, the photocathode is this metal that light from the LED is going to hit in an attempt to eject electrons from it. So, of course, the light from the LEDs travels down, focuses by the lens, goes into a little hole on this aluminum box here where that photocathode is, and starts perhaps the photoelectric process to begin, and we can study it. Apart from those things then, what we have over in the corner here, as you can see here, are a couple of instruments here. This one right here is the Pico Ammeter. One of the premises of getting the photoelectric effect to work or to study it is we like to stop all photocurrent, and being a Pico Ammeter, this can verify sort of a zero-ish current down to a fraction of a nanoamp or into the picoamp. So we refer to it as a Pico Ammeter. So we'll see how that works when the data comes along. And sitting right on top of it, although it doesn't need to be on top of it, it just is at the moment here, is a small power supply. This actually just has a battery in it, and if I turn this knob, it'll supply voltage between 0 and 3 volts. And this is connected, as you can see, directly to the box that contains the photocathode, and this will be our stopping potential. So when the light goes into this box and hits the photocathode, electrons will try to come off, and as you'll see, to get the photoelectric effect to work or to study the effect of the wavelength dependence on all of this, we try to stop the electrons coming off by applying a voltage to the photocathode, which is exactly what this box is for. So it's called the stopping potential because we try to turn it up high enough to stop the electrons from coming off the photocathode. And of course, the degree that we're able to stop the electrons, in other words, a flowing of current, is measured on the Pico Ammeter, as mentioned. So lastly then, on top of the stopping voltage box is an ocean optic spectrometer. This is sort of a generalized device that tells you what wavelength of light you're sort of using. So the way that'll be used in this experiment here is, although the LEDs are pretty well characterized and even labeled, the wavelengths on this box aren't quite the emission wavelength of the LEDs, and we need to know exactly what that wavelength is going to be in order to pull off the photoelectric effect. So what you do is you just sort of move this right in the way of the LED as you start your measurement like that. And so what will happen is the light from the LED is, of course, blocked from going down the rail, goes into this blue fiber here, and when it goes into the blue fiber then, it of course enters the USB spectrometer that's connected with a USB cable over here to the computer that I have in the back. And if I zoom in on the computer screen, what you can see there is sort of a peak here that represents the emission, the wavelength emission of the LED. So you can see it is fairly narrow band. There's a central peak, which will be the central wavelength you'll likely focus your attention on, and there is some bandwidth in there. And so what this spectrometer allows us to do is determine the wavelength of the LED that is being aimed at the photocathode. And so the step-by-step data taking will be, we'll select an LED to use by turning this knob here. We'll get its wavelength using the ocean optic spectrometer. Then we'll go over here and we will turn up the stopping potential until down to a fraction of a nanoamp, into the picoamps. We can demonstrate that we are stopping the electrons from coming off the photocathode with the stopping potential. That's going to essentially be our data set. So that in sum is all the equipment needed to pull off the photoelectric effect experiment. Again, one more time, a wavelength is selected. The photocathode is irradiated with that particular wavelength. We try to stop electrons from coming off the photocathode using a stopping potential, and we verify the stopping of that photocurrent using a Pico Ammeter. So we verify no electrons are coming off down to the fraction of a nanoamp or into the picoamps, and that will form our raw data. So in subsequent videos, we're going to look inside this metal box to see what's inside of there. Then, of course, we'll start our data.